here we've got a couple of charts. This one's telling us what the magnetic field is doing over time, and this one is telling us what the charge is doing as it's going through this point P per second. Now here we can kind of figure out what the current is because we'll have Q over S, and so we'll be able to figure out what that current is going through this. And we're asked to find the resistance, so that's interesting. But I think we do know a rule that says something like, if we're trying to find resistance, we can use something like this: R equals epsilon divided by I, right? Because IR equals epsilon, so you can kind of rearrange that and get this equation. So let's go ahead and try to find what this EMF is. I think we can do that. And that should be the negative time derivative of the flux. Now let's try to set up the flux equation. So that would be like the integral of B dotted with dA. Now we should be able to figure out what this B is by looking at this graph. Well, at the beginning, B is 0. And then towards the 3.1 second mark, B is 9.8 milli teslas. So we could figure out if we said 9.8 to negative 3, and then we kind of divided that by 3.1 seconds, then I should get a slope. So essentially I'll get like that B is equal to 3.1613 e to the negative 3, and then I'll put a T over here, kind of like an X, because if I multiply that by 3.1, I get that. So I'll just call that this, and I can plug that into this equation here. And then I also know this dA thing. Apparently, they've given us the area as being 9.4 e to the negative 4 meters squared. So we'll go ahead and just kind of put that in there. Well, let's try to rearrange this equation a little bit better. I would like to say that I can kind of technically consider this B constant. So I'll go ahead and pull that out, and we'll solve that integral of the dA component, which we have solved, which is that, because I could say this equals the 9.4 e to the negative 4 meters squared. So technically this part has been like taken care of. So now we can just say 9.4 e to the negative 4, and then whatever B was, which is this 3.1613 e to the negative 3 t. Because this is all a constant. I mean, the area doesn't change over time, so the time isn't going to be like included in this integral. So we've basically just kind of solved the integral separately here. This was a given, and then now we'll just plug in this B over here. So we're looking at the flux being equal to this. Now we'll go ahead and take the negative time derivative of the flux, which should give us the EMF, right? And so we'll just take the negative time derivative of this, and that means that we can just get rid of our T. So here I'll be able to just say that the EMF is equal to 9.4, and this is magnitude. I'm going to exclude the negative sign, but e to the negative 4 times the 3.1613 e to the negative 3. And then if I wanted to solve for the resistance, we'll divide this by the I. So just divide this by Q over S. And this should be equal to the resistance. So let's go ahead and try to figure that out. So we'll go 9.4 e to the negative 4 times 3.1613 negative 3. And then here on the bottom, we'll go 9.2 negative 3 divided by 3.1. And perfect. We were able to get the resistance being equal to 1 milli ohm. All right.